In this video, we're going to be talking about some 2D examples for pin and support reactions. We're only going to go through 2 examples just to make it nice and short, since we already got a lot of practice from the notes video to solidify concept. If you'd like, there are these other problems here. So I'll kind of just stop on each one. This one's not finished yet, but I'll stop on each one so you can take a screenshot. If you'd like to work on it, answers are included, but not the solution. So see if you can figure it out. The reason I am skipping these ones is because the geometry does take a little longer, and I'm confident you guys can do this on your own. So I'm going to break apart these two. This one has a little bit more complex geometry going on, but let's start and warm up with this one. Okay, so what forces are going on here? So let's identify our reaction forces. We've got a hinge. So we've got 2 forces here, AX and AY. And at this pin, we can have B and C that look like that, as well as our moment. But instead, we know that we can use 2 force members. So let's just imagine this as a 2 force member that is directed this way. So let's pretend we have that. So this is going to look a lot cleaner now, because now we have only 3 unknowns rather than 6. So let's call this FBC, some important geometry. We have 30 degrees with the horizontal. We've got AX and AY, as well as a free moment acting clockwise, 500 Newton meters. Okay, so that's how we use 2 force members to quickly simplify a complex problem. Same as always. Let's do our Fx, Fy, and moment. So this has a positive x direction, FBC, of cos 30. Fy, we've got AY, and our FBC is in a positive direction, positive y direction, sine 30. And when we take moment about A, we're choosing A because it has the most reactions going through it. So that only leaves, so we're going to add this free moment in here, so don't forget about it. And then that only leaves our, I'm going to do this in a different color. I'm going to do this in a pale green so you can see. So this is our X reaction and our Y reaction. So in our vertical reaction, so that's FBC sine 30, we want our horizontal distance. So from B to get to A is 2 meters. So we're going to throw that in there. And we would be going counterclockwise to get there. So that's plus. Then we have our horizontal component. And this is at a vertical distance of 1 meter. And our direction would be in a positive direction. So we go counterclockwise to get there. Okay, so let's solve for our FBC from our moment equation because we have all of our values already ready. So let's move that 500 over to the other side. Let's factor out the FBC. So then we're left with 2 sine 30 plus cos 30. And that makes FBC equal to, so let's take 500 and let's divide it by 2 sine 30 plus cos 30. And this becomes 267.949 newtons. and this is positive, so the direction that we assumed for our FBC is correct. So I'm just going to draw the direction of our arrow. If we check our answer, indeed that is not on here, so give me a second. Okay, so this is the diagonal components. This is the vector of FBC, but since it wants these support reactions at pin C, we're going to have to decompose our force here. So to get Cx, we would have to take 267.949 and take cos 30. And this makes it 232.050 in our positive x direction. And for our Cy, is equal to FBC sine 30. So we're just breaking it out into their x and y components, and this becomes 133. In our upwards direction, since our first initially assumed direction is correct. Right, and that gives us these answers here. So we're in good shape for those ones. Okay, and now we can solve for our A reactions. So let's do just that. So let's solve for AX. So AX is equal to negative FBC cos 30, and this gives us a negative quantity of negative FBC cos 30. This is equal to the same as our Cx value, but in the opposite direction. So AX would be equal to 232.050 in the negative x direction, so opposite to what we first assumed. And when we solve for AY, same thing, AY is equal to negative FBC sine 30, and that's going to be AY is equal to 133.974 in our downward direction, opposite to the direction that we first assumed. So that's how you can use two force members to break down our components, right? And we were able to achieve this because we could find FBC as one variable and then just use our geometry to figure out the rest. Because if not, we would have 4 unknowns and 3 equations, which isn't possible. So that's why we had to simplify it first and then go forward. Another way you can look at this is by breaking this down into 2 sections. So going from A, B, and then B to C, and writing out 3 equations for each of those beams and then kind of relating them to each other. That may work better for some other cases, but in this case, 2 force members is the most straightforward way to go about it. Okay, so lastly, we have this problem here, and we want to find the reactions at roller B and pin support A. So we have 3 unknowns, so we have 3 equations that we need. So at our A hinge, we have AY, AX, and we have a normal force of B at this roller. All right, so we're also working with distributed loads as well. So let's start just simply with our rectangular one. This is 750 newtons per meter times 1.2, so the length that it spans. So this is an equivalent force of 900 newtons acting at 0.6 meters. Okay, so this one's got lots of angles going on, so we got to be careful. Okay, and I'm going to find what this height is. Actually, no, let's do that after. Okay, next I'm going to work with, so we're going to divide this into two sections. So we're going to have a triangle section and a non-triangular section. So if we work with our triangle first, this is at a height of 750 newtons over 1.8. So then our force is going to be the area of our triangle, 750 times 1.8 divided by 2. This is 675. And it acts at 1/3 of our length. So if we take 1.8 divided by 3, this is at 0.6. 0.6. That is from our triangular one. And in pink, I'm going to do this section here. So this is going to act at our center of our beam. We already know that. I'm going to call this point D. This is at a distance of, God, this is so messy. I apologize. A distance of, so it's half 18, that's 0.9. And this is, our height is 750 over a length of 1.8, and that gives 1.8 times 750, so it's 1350. Okay, so there are all of our forces. So, little geometry. Let's work through it. So on our beam, we have 675. This is 60 degrees. So let's break our components up. And let's break up the length of our triangle as well. Hold on. I'll draw this neater. So if point C is at the top of our triangle, then our geometry, so this is 0.6 meters from A. I'm just going to do some rapid fire geometry. So that's sine 60 times 0.6. This is 0.51961. And then cos 60 times 0.6 is 0.3. So that represents this triangle here. And some other geometry about this 675. Going to find the x and y components. So this is 675. This makes a 60-degree angle. So that means, this means that we make a 30-degree angle, the horizontal here, if I'm not mistaken, and thus a 30-degree angle here. Okay, and with our pink force, so this is point D. So it acts at 0.960. So then let's do some more trigonometry. This is 0.77942. And 0.9 times cos 60 is 0.45, distance here. Okay, and this also acts at the same kind of geometry where we make 30 degrees like that. Okay, so now we have everything that we need. So let's start out our equations. So we have ax, and we have our x and y components of our diagonal forces. So these are both in the positive direction, so 675, and that is cos 30. And we have our rectangular distributed load, which is positive x direction again. This is 1350 cos 30, which is equal to 0 altogether. And then we have our Fy directions. So then we have negative 900 acting downwards. That's from our top of our beam, the flat part. This is plus our normal force of B. And we have downward forces for both of our diagonal ones. That's minus 1350 sine 30, right? Because it points downward. Okay, and sorry, almost forgot our AY, plus AY. Okay, now this moment one's going to be a little tricky. We're going to start our moment at A. You want to be careful with this one. So let's start with 675. And let's use our horizontal. So we need to find the vertical distance that we need to get in order to get to our, let me just clean this up a bit. In order to get to point A, so we need our vertical distance. So our vertical distance is from here to here. And we found, okay, so let's make another triangle in red this time. Let's do our whole triangle, then you're going to subtract this distance here. So as a whole, this triangle is equal to, so it's 1.8 times sine 60. So this is 1.558. And cos 60 times 1.8 equals 0.9. So we're going to take our full height and we're going to subtract our y value from our blue triangle, which is 0.51961. And this is in our, so we'd be traveling counterclockwise to get to A. Oh, sorry, to get to A. My bad. That'd be my bad. Hold on. Okay, sorry. We're starting at point A. We are at a distance of 0.516. Okay, let's try again. Horizontal component at a distance of this blue height to get to A is 0.51961 meters. And we'd be going in our clockwise direction to get to A. Apologize for the confusion. Okay, and our vertical component, we want our horizontal distance, which is 0.3. And we would also be going in a clockwise direction, so negative. Okay, so then we can start with our 1350, sorry. So cos 30, This is our horizontal, so we want our vertical distance, so that's 0.77942 clockwise. Same thing for our other one. We want our horizontal distance for our vertical components, so that's 0.45 to A. Okay, and now for our 900, so I'm going to have to do this on the next page. We zoom out a bit so we can fit everything in there. So for our 900 newtons from our distributed load at the top, we want our horizontal distance. So we have 0.6 from our diagonal part, and we want to add to that with our 0.9. That will get the correct distance, and that is clockwise. So it's negative. And this we will need to go counterclockwise, so that this is plus for our NB. And we want our horizontal distance again. So we have 1.2 meters from there. And then we have to add the 0.9 meters. Okay. So let's solve for NB in our moment equation. So I'll be back with the calculations. So after we moved all of our negative terms over, that gives us 2,969.994 is equal to NB, and 1.2 plus 0.9 is 2.1. Right, and if we take that value and we divide it by our 2.1, our normal at B is equal to 1,414.283 newtons, and it is positive, so the direction that we assumed is correct. And let's check. Yep, so that is the right answer for our normal force at B. Looking good. Okay, so let's divide the rest of this off. Okay, and let's solve for our AX. It's an A, sorry. So AX is equal to negative 675 cos 30 . Actually, we don't even need NB to solve AY. So this is equal to 75 cos 30 . And AX is negative 1,753.701 newtons, or we can express this as magnitude with a little direction. So this is 1,753.701 newtons in our opposite assumed direction. So there is AX, and AY is given by, so we want to find AY, so AY is equal to 900 minus NB plus 675 sine 30 plus 1,350 sine 30. So let's plug that all in. So that's 900 minus our solved NB plus 675 sine 30 plus 1350 sine 30. And this gives us AY equal to 498.217 in our positive direction. So that means our assumed direction was correct from the start. And there are the three values that we just solved for. All right, and those are correct according to our answer key, so we are good. So always be careful when you have some complex geometry with your beams. and make sure you're careful with formulating your equations according to direction. All right, so that brings us to the end of this video for practice problems. Like I said, you can use the other ones in the video to practice with, and answers are included so you can check your solutions. And yeah, I hope you enjoyed, and I will see you in the next one.